Okay, good morning, everyone. Lecture 3. And today I'll discuss a bit on the details about the specific form of this superconducting density current. So this current that we showed yesterday, we had essentially this expression, I QS H bar over MS, twice MS. And here we have the wave function, the gradients of the wave function conjugate minus wave function conjugate the gradient of the wave function minus QS to the square over MS. And then here we have the absolute value of the wave function times the vector potential. Okay. So as I mentioned yesterday, this superfluid current, allows us to explain some effects like the Meissner-Ochsenfeld effect. So this effect has to be with the perfect diamagnetism. So we will see this later with a specific example. Why, I mean, the appearance of surface persistent currents immediately. What happens is that if we apply any magnetic field to some superconducting sample, the sample will expel everything. So that inside the superconductor, we have a zero magnetic field. Okay, so the idea is to find an expression for this superfluid current, and the starting point is because we have the continuity equation. Remember that we have the partial derivative of the charge density rho of x of t equals to minus the divergence of this superconducting current. And the idea is to use the definition we have for this superfluid charge. So the superfluid charge which is this rho of x comma t. This is nothing but the Cooper pair charge QS and the modulus square of the macroscopic wave function. Of course, then the main idea is that we should take what we have. We can run a lot. So we should take the derivative rho. This is nothing but, so we take this expression, okay, we take this expression, and then we take the partial derivative, so that we have derivative of the wave function times wave function conjugate plus the wave function times the partial derivative of wave function complex conjugate. And then what matters here is that we should use use the Schrödinger equation. And the Schrödinger equation tells us that I h bar, so here we have an expression for the partial derivative of the wave function, which is essentially 1 over 2 ms. Here, remember, we have the minimal coupling because we have a charged superfluid essentially. The momentum. Then we have the product of the Cooper pairs charge times the vector potential. This is to the square plus QS and the scalar potential B times psi of x comma t. So indeed, you have to be careful here because this is an operator that should act on the wave function. Okay. So I mean, this is a bit tricky sometimes. So I prefer to show the calculation. So we have this is the partial derivative x comma t. So here this momentum, the minimal coupling to the square should be written in this way. So we have 1 over twice ms. So this quantity we have here to the square means the following operation. So this is minus I h bar the gradient operator minus QS AS. This is dot, and the same quantity minus I h bar gradient. But you see that, I mean, let me put it in this way. And so here, we should multiply by the wave function. So first of all, we have this operator will act first on the wave function. And then later, we apply this operator to the rest. Okay, this is the idea. So we have this expression plus QS, the scalar potential B times the wave function. So we have 1 over twice ms. So we have minus I h bar, this operator minus QS times A dot. So here we have minus I h bar, the gradient of the wave function. So I'll remove the dependence, okay? I will avoid to write this part just for me for simplicity, essentially. And then we have a minus QS times A times C plus QS B psi. And then what we have here is twice 1 over twice ms. And then we have, first of all, we have this operator acting here. So there will appear a nabla square. And we have a minus h bar to the square, nabla square over acting on the wave function. Then we have a term which is this with this. Then we have plus I h bar qs, and then we have this operator acting on the product A times the wave function. Then we have this term, this and this, okay? So in this case, we have plus I h bar qs A dot. So this is the gradient of a scalar function, this part. This is the gradient of a scalar function. So in general, it will produce a vector field. And the vector potential is also a vector field. This is why we have a dot in between. Then the last term we have is plus qs to the square, the vector potential to the square times psi plus qs b psi. And then, well, you see already we have from this last equation that we have here. So everything that would be on square. So this allows us to have essentially the derivative of the wave function, and we can plug this into this part of the above equation above. Of course, you can produce the similar result. So you take to this equation we have here in the box, you take the conjugate to the whole equation, and then you will have an expression for this part. And of course, after a bit of algebra that you'll see in the appendix that I will provide, at the end of the day, you should prove something like this. You can really find something like, so essentially you form by trying to form the continuity equation, you should be able to prove that after all the algebra, you will have something like minus the divergence of a quantity, which is exactly the quantity that we need to find, which is essentially the superfluid superconducting current density. Minus qs squared s module square. So probably the most, I mean, sometimes I like to show this calculation because working with this term to the square and acting on the wave function, sometimes it's not trivial. I mean, one could produce some mistakes here if you develop first of all the if you don't take care of how the operators act on the scalar field, which is in this case, the scalar field is the macroscopic macroscopic wave equation, and the vector field is the vector potential, essentially. Okay. So this expression we have is the superconducting current density. Do you follow the calculation?
Yeah, I will ask you about, because you need to consider a special kind of a vector potential, or
Nothing. And until this very moment, this is completely general. Nothing.
Okay. I think that, because I would like to ask you about if you consider as a real or a complex one.
I mean, this is in general should be I mean, this is a vector potential, which is you can find the vector potential even or the scalar potential written in the 3D space. So it should be a real quantity. So it's a real vector field in general.
Okay.
But at this very moment, yes, typically this should be a real vector field. Okay. Okay, so let me. So as I mentioned yesterday, well, we have this superconducting density current that essentially allows us to explain why there appears this effect of a perfect diamagnetism in a superconducting sample. Well, we have to carry out a little bit more of lectures, but we will apply this to a specific case where you will see that you can really find, well, first of all, we need to find, we found already an expression for this superconducting density current, but then we also need an equation for the superconducting phase. And then from that, we will show the famous London equations. And the London equations tells us that any the superconducting currents, they live on the surface of the superconductor, but also we will show that any magnetic field that try to enter the sample will decay exponentially, essentially. Okay. But for this, we need to show a little bit more on the I mean, we have to find an expression right now for an equation for how the phase will evolve in my system. Because as I mentioned yesterday, we have, let me continue here. So let me discuss a bit on the superconducting phase, because we know that the macroscopic wave equation. So in general, we have this expression. Remember that in general, we have the amplitude has to be with square root of the density of the charge carrier, which are the Cooper pairs in this case. Okay, and we have a phase here. This is my famous superconducting phase. We also mentioned that an important approximation that we will work with is that we always assume that this density of charge carrier is more or less homogeneous along the superconducting sample. And the reason for that is that the superconductors, they approach charge neutrality, okay? And because you have charge neutrality means that the electrons should be distributed on along the surface, let's say along the sample, such that they will cancel any charge of the ions in the lattice. Okay, if this is the case, so if this charge density is homogeneous, let's say there is no space dependence nor time dependent in this case. So it is quite clear that the only relevant part, I mean, all the information, all the dynamics of the wave function has to be with the phase necessarily, because this term is constant essentially under this approximation. So then first of all, let me show you what happened if we assume this approximation here. Specifically, let me show you what happened with the superconducting density current that we showed previously. So this density current, superconducting density current, is I US times h bar or twice ms. Here we have a psi gradient of psi conjugate minus psi conjugate gradient of psi minus US to the square ms module square A. And then, of course, here will appear a constant term. It is quite clear, no? Because the module square of the psi. So in this case, this quantity is nothing but the density of charge carrier, which is constant under this approximation. But we need to know what happened with the gradient of psi. Of course, this is this case we have the gradient will act on this operate. I mean this the phase only. And here we have I and s to the square. And here we have the gradient of the phase e to the I theta. So we can put together this term times this term is again the wave function. So we have I, the gradient of the phase times the psi of x comma t. We have this part. Of course, then it is clear that if we take the gradient, so we take the previous equation and we take the complex. And what we obtain here is, of course, we have minus I, the gradient of theta. So, of course, theta is a real number. It's just a phase. And then we have this quantity. And then we plug these two equations into the superconducting intensity current. We have I, QS, H bar, twice MS. So psi is square root of NS, yes, and the gradient of psi conjugate. So meaning we have minus I, the gradient of theta. Sorry, let me put everything together, okay? So we have psi, which is square root of NS e to the I theta of x comma t. Then we have the gradient of the wave function conjugate, so times minus I theta, gradient of theta x comma t times psi conjugate. You see? And the important thing is that psi conjugate will introduce this quantity is nothing but square root of ns e to the minus I theta. And this e to the minus I theta will cancel this one. You see? Then what else? We have minus psi conjugate and s e to the minus I theta. And the gradient of the psi, that is I gradient of theta and the wave function. So it means we have this quantity, minus I QS H bar over twice MS. And here we have the first term, we have minus I NS gradient of theta. This is the first term. Then we have again minus I and S, the gradient of theta. Sorry, I forgot to plug this additional term here, which is QS to the square over MS. Modulus square of the psi, which is N, essentially. So let me put here, this is NS times the vector potential. So I'm talking about this last term here, okay? So this is minus QS to the square over MS, NS, the vector potential. So we have these two terms are equal, and then we have twice this term, and the two cancels with this two that appears here. But then we have the sign that we have here is, sorry, here I made a mistake. This is a plus sign, okay? That comes from this term. So we have a I times I, which is minus, with minus is plus. So we have a QS and S H bar over MS. And here we have the gradient of theta minus QS to the square and S over MS times the vector potential. So here there appears something really interesting, that in the case of a homogeneous, so this is an homogeneous charged superfluid, we can factorize how if we factorize QS and SMS, here we have H bar, the gradient of theta minus a QS. So this is like this is a momentum. This part has dimensions of momentum. Here we have a mass. So this is a velocity. We can define a superfluid velocity here. This is QS and S. And let me put in this way much better with the notation. The S, which is nothing but the superfluid velocity. So this is essentially the, like you have in your course of electromagnetism, you have a fluid, no? And then the current, the density current of the fluid, you need the charge, the density of charge, and the velocity. This is called superfluid velocity. You see this, no? I mean, we have, then we have this relation. So again, I mean, this happens if and only if we have an homogeneous superconductor where all the, I mean, we have an homogeneous charge distribution of Cooper pairs along over the superconducting sum. So let me now because we have, so we are essentially what we are doing is essentially what we are considering this. We consider this condition here, and then we have a particular expression for the macroscopic wave function, where all the information about the dynamics has to be with the superconducting phase. First of all, we can relate the gradient of, so any spatial fluctuation in the phase, so here, has to be with the superconducting density current. Okay, this is interesting. So then I mean, in this this is something really something sometimes not very intuitive as compared with the usual quantum mechanical system we we study, for instance, I don't know, a particle in a box, etc., where the phase is just a number. Okay, but here we have a physical interpretation. So that is a gradient of the theta. So any spatial variation of the superconducting phase involves some kind of a movement. So because then you have a superfluid charge current. See, this is interesting. So what else? What else? Indeed, this is one of the first equations that we will use for describing the electrodynamics of any superconductor there. Indeed. So keep in mind this equation, but anyway, I'll show you later. Okay. But keep in mind this equation because then we need to know what happened if with this condition we have in this part what happened with the Schrödinger equation. Okay.
I have a question.
Yes.
When you consider the sample, there are not Cooper pairs flowing outside the sample, right?
No, on the surface.
Okay, because I'm trying to imagine that system where the Cooper pairs are equally distributed around the sample, but they are moving around it or not because the charge current.
I mean, they move around of course they move, but on the surface. You can prove, well, it depends, no? I never talk about this, but it depends on the interface we have. Superconductor with something else. And then if you have superconductor with vacuum, you can really prove that there is no current flowing outside. Okay, there is no components of the current flowing perpendicular to the surface.
Okay.
And then you move around the surface only.
Okay. I was thinking about inside the sample.
No, on the surface.
All in the surface. Okay.
All in the surface, because inside, if you go deep into the superconductor, there is no indeed we will prove that this density current also decays exponentially as well. And there is a characteristic length, which is the London penetration depth. So always the superconducting current lives on the surface of the superconductor.
Okay, thank you.
You're welcome. Yes, we will show this with an example, okay? And then you can really see that if you compute this superconducting, this is interesting, this superconducting density current, it decays exponentially. So they penetrate, and if you have, well, if you have a very wide superconductor, then at the bulk you will see nothing, any current, okay? But but it depends. If you have a very narrow superconductor, maybe yes, maybe still you will have some current inside. So it depends, essentially. And sometimes you have to take care of this because there is some kinetic, that people call kinetic inductance, that has to be with the superconducting electrons that flow inside the superconductor, because the superconductor is very narrow. Okay, this is interesting as well, and people use this. For instance, this is one of the mechanisms to reach ultra strong coupling, for instance, in superconducting circuits, with when you couple a flux qubit with a coplanar waveguide resonator. They put, I mean, in the coupling, when you couple this flux to the coplanar waveguide resonator, there is I mean, the resonator is very, you have some width, but then at the central part where you plug the superconducting circuit, the wire is very, very narrow, so that you have to take care into account the current that flows inside the wire in that case. And because you have this, people call this kinetic inductance, and then because of that you increase the coupling with the coplanar waveguide resonator and the flux qubit, for instance. But again, it depends on the the size, the width of the superconductor. More comments or questions?
No.
Okay. So let me go through a bit more, and now I'll show you that you can relate the. We have an equation here for the gradient of the phase, but we need an equation for the partial derivative with respect to time of the phase. And this equation, you'll see it is related to the scalar potential, B. So, so the question is, what about an equation for this partial derivative with respect to time? And first of all, this is, I need this for the discussion. Let me fix a particular gauge. So this is very interesting because if we suppose we fix a gauge, sorry. The Coulomb gauge. Meaning that suppose the divergence of this vector potential is 0, essentially. And if this is the case, then what happens here is the following. So if I take, suppose we take this equation we have for the density current, and then I take the divergence of the density current, meaning we have QS and S and S, H bar now the square theta minus QS divergence of A. So if we are if we work in this particular gauge, this is 0. Okay, so meaning this divergence is nothing but QS and S and S, H bar and nabla square of theta. But remember that we have the continuity equation. Yes, plus, so the derivative of the charge density plus the divergence of the density current, this is 0. Okay, so since for us this density current, remember that we have, this is a QS module square of the macroscopic wave function. Remember that we assume that we have an homogeneous superconductor. The charge density is homogeneous. So this modulus square, so this charge density, of course, should be homogeneous. No, no time dependence, no space dependence. So meaning that if I take the derivative of rho, this is 0, of course, under the approximation we have in mind, okay? And it means, because of the continuity equation, that the divergence of the density current is 0, meaning it implies that we have the Laplace equation essentially for, so under these conditions, the phase satisfies the Laplace equation essentially, because you plug, this is 0, okay, here this is 0, and this implies this condition here. So keep in mind that we have divergence. We choose this particular gauge. This divergence of A equal to 0 implies that the phase satisfies this Laplace equation. So we have the macroscopic master equation. Sorry, I'm confusing the lectures. Open quantum system. The macroscopic wave function is this quantity, square root of ns e to the I theta. And then we'll replace this into the replace this form into the Schrödinger equation. We have to replace this into the Schrödinger equation. So remember that we have I h bar derivative of the wave function. This is the in general, okay? This is 1 over twice ms. Here we have, sorry, minus I h bar nabla minus qs times a to the square acting on the wave function plus qs. This is the vector, the scalar potential, okay, times c. So replace this form that we have here. So if you see, if you take this form, it is quite clear that if I take the derivative of the wave function, it for sure will involve a derivative on acting on the phase, because we have to take the derivative of the exponential function, and then it will appear a derivative of the phase. Again, this is a calculation which is a little bit long. It's not so long. You can see the specific calculation in the notes later. But I mean, you have to be careful again with the action of this operator, okay? That to the square acting on the wave function. This is the only thing that you need to be careful on that. But then here, prove the following. So this is an exercise. Prove that there is the following equation that we can relate. So minus h bar, the partial derivative of the phase, x comma t. This is equals to a parameter lambda that I'll define later, twice and s. And here appears the density current to the square plus I'm using this notation, so x comma t plus the qs, the scalar potential. So you need to prove this relation here where this parameter is defined as ms over qs square and s. And this parameter is called the isotropic London coefficient. Oh, look, this is an interesting thing because let me, so we have this equation, the one here, the red box here. So we see that any spatial fluctuation of the phase can be related to a superfluid current, you see? But here, if we take and plug the microscopic wave equation, assuming that we have an homogeneous superconductor, then what we see here is that the derivative, the partial derivative with respect to time of the phase is what? Have a look. This is a charge and a scalar potential. This is nothing but the electric energy in the system. So it has the dimensions are of energy. And this part that has to be with the current to the square is the magnetic energy. So this is really interesting as well, because then now any fluctuation in time of the phase is related to the energy of the superconductor, you see? And a particular case, so you see that these are, but how look, we are working in a specific gauge, which is the Coulomb gauge, okay, first of all. And then what we see here is that if we have no supercurrent, superconducting. So imagine for a moment this situation. Imagine that we have no superconducting currents over the on the superconductor. So it means that I can tell that the derivative of the phase can be exactly related with minus QS over H bar, the voltage. the scalar potential. Okay, we have this relation, and this relation is called a phase voltage relation. Well, not really for voltage, okay, but because we have that the partial derivative with respect to time can be related, or of the phase is related to the scalar potential. At this very moment, I mean, this is just a curiosity, but later on, we'll see that the dynamics of a superconductor, meaning the phase, has to be with something that it is related to the scalar potential right now. But then have a look. This phase voltage relation we have here is not gauge invariant indeed, because remember that this scalar potential B, this is defined up to the partial derivative in time of a scalar function. I'll show you later in the next lecture. Okay. So then what I'll show later is that there is a really phase voltage relation, but the phase is not this exactly this phase, but it's something that is called a gauge invariant phase. And the gauge invariant phase will be related to the voltage difference between 2 points in the superconductors. And this is really, really important, because it means that it will put the specific tool for how you will describe the dynamics of a circuit involving superconductors. Later on, we need to define what are the voltage differences in my circuit, and then I will be able to relate those voltages differences to the dynamics, to the internal dynamics of the superconductor. Okay. And this, keep in mind this, because this is very important, because later on, when in the next topic, when we describe superconducting arrays, we need to identify let's say the internal dynamical variables in my system. And dynamical variables has to be with the phases of the superconductors. And the phases of the superconductors will be related to voltage differences in my circuit. This is why this phase voltage relation is so important. But at this very moment, all this derivation we did here is valid for a specific gauge, which is the Coulomb gauge. We need to prove later on that there should be a relation which is gauge invariant. Okay. And that will be the next task for us. And that will appear the concept of gauge invariant phase. The only task you need to prove here is prove this equation we have here, following a little bit of algebra. Okay, but you can really prove these two equations. So this one has to be with the partial derivative of the phase and the gradient of the phase. So I'm not sure whether this is clear at the moment, or maybe what is not. I mean, the derivation is more or less clear, but I mean the presentation maybe, or the underlying fixes that I'm trying to pass, maybe it's not so clear. But I'll show you, I promise that in the next lecture, when we introduce the concept of gauge invariant phase, you'll see that any partial derivative of the phase, the gauge invariant phase, is related to the voltage difference. And then these voltage differences are physical quantities, right? Because you have it in the experiment. Okay, that would be important for our next discussion when discussing, I mean, the theory of circuits. So, is there any comments?
Not for the moment.
Okay. So next week I'll show you this general relation, but for I mean, for gauge invariant cases. Okay.
Okay.
Okay. So with this, I finished today. I'll send you the notes right after this finishing this lecture. Okay. So that you can really follow the calculations.
Okay.
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 Goodbye.
Thank you.
See you next week.
Next week. See you.